I don't think I turned it at all for that, so oh well, too bad. Let's see. So the other half of this section, actually, the homework is like mostly based on this. It's called differentials. Now just go with me for a second. If I had a function and I have a point A, and I have this tangent line. Oh well, too bad. You sound like a straight crap and a half. If I was OCD, I would so hate myself. All right, so here's. Let me back up just a second. Let's call this. We'll just go ahead and call it we'll call it x. This here is x plus delta x. Okay, I really should have blown that up a little bit. All right, you guys with me so far? I mean, nothing major there. All right. So the blue line, again, differentials are really tied very closely into what we just did with the linear approximation. The closer I am to the point itself, the better my tangent line is at approximating things. That's the basic idea. So here it's going to feel very similar. We're just going to better define some notation we've been using this whole time. This officially here, this much is what? What's this?
Change x. Or change delta.
Yeah, delta x, I'm with you. Delta x. What's this going to be then?
Delta y.
Good. That's y, and that's y plus delta y. So that's delta y. So up here, this poor dude, that is actually dy. So let me make a few things a little more clear. So when Leibniz did his whole thing, he based everything on ratios of differentials. With me so far? So I think I said that at some point earlier when talking about history. Right? Whereas Newton said, no, you're crazy. And he did his own thing. Right? So dy and dx both refer to the tangent line. Is that cool by itself? Delta y and delta x, I might as well keep the theme going. Delta y and delta x refer to original function. You with it? Because delta y is the true change in y. dy is actually what the tangent line is doing at the point. And y, earlier I kept saying that dy and dx were infinitesimally small changes in y and x. And now you're like, that is a pretty big ass change. So that's because the tangent line is a straight line. What is the slope of this tangent line? I like the some number. But now give me a symbol for it. Yeah, slope of the tangent line at x. I like that. At that point x would be f prime x. With it? So if I say dx is this change in x, how much, and I go, so I'm a dx, let me see if it works. How do I connect dx and dy together? No? So dy will equal f prime of x dx. So the change in my tangent, and again, it's because the tangent line in blue is just a straight line. So how do I figure out how much y is going to change? Well, I just multiply my change in x by my slope. That'll tell me how much y changes, right? Is that cool? Multiply my change in x by my slope, I get how much y changes. So this truly is the idea of differentials. This is going to become huge when we start learning integration, which is anti-differentiation. It's the inverse function. Right? Big-ass words, but nowhere near as weird as the thing as it sounds. At least not to start with. All right. Now, again, I can't stress this enough. It sounds way harder than it actually is. I can't say that enough. If I want to look at it in terms of delta y and delta x, let me do this better. What should I call? I should call that f of x, and I should call that f of x plus delta x, right? Is that cool? So what's delta y in terms of those two? Delta y is the what of these two? The difference. Okay, cool. And that should look roughly familiar. It looks a lot like the limit definition function thing that we use where delta x would be h, right? Okay, we're not going back there, don't worry. We're not going there. Okay, so what does this lead to? So, for example, let's try a problem out of the homework. So when it says, for example, if it says find a differential. So right here, we just showed that if y equals f of x, dy equals f prime of x dx. Now, yes, I don't know if any of you guys have noticed this. If you divide by dx, you get Leibniz notation and Newton notation connected, right? dy over dx equals f prime of x. Kicks ass. And again, I can't stress this enough. It's because the tangent line is a line that it can kind of extend these guys' meanings further than they really should because it stays the same. The ratio is the same. It's a stupid line. dy over dx doesn't carry. That's why Leibniz went that way. Newton had trouble with differentials. He's like, they don't really exist. That's bullshit. And then he went a totally different way. And they come out being the same damn thing. It's neat. That's the history guys. So let's see. Let's look at number, what did I say, 11? Y equals x squared sine 2x. Okay, so this is actually so desperately nothing new. It's crazy. But it's just getting used to writing derivatives in a form you're not used to. It's just one step away from what we normally do. So to find the differential, you say dy equals, here's f, so how do I find the differential? Dy is f prime dx. So what's f prime? How do I find this guy's derivative? What do I have to use? Product rule, good. So you have x squared prime is 2x sine 2x plus leave x squared alone. Derivative of sine 2x is cosine 2x times 2. And what do you put at the very end? dy equals f prime of x dx. Cool. Now, I'm going to write something on the board that I'm going to reference when we get to the end, the very last section we're going to do this semester. I'm going to say, remember that day that I'm saying exactly what I'm saying right now? That's going to be a weird day. Remember when Jeff of the past was referencing Jeff of the future? So if I had like u equals, what you got, Jeff? I don't know. They're on there. Natural log t. Find the differential. How do you find the differential? We just did it. It's nothing major. No, I don't see any y. du. It's okay. I'll think about it. 1 over t
times dt.
I love it, sweet. I mean,
I redeemed myself.
you did, totally. That's the differential. It's almost stupid. I mean, how would I do Leibniz notation on this thing? I say du dt equals 1 over t. If I just multiply the dt up, I get that. Right? I mean, that's simple. Somehow that's going to become very stupid important when we get to integration. And I want you right now to realize how simple that is. When I say find the differential, bam. Later in calculus, you have things like the exact differential and the total differential. So it's going to build on this idea. And it's normally for possibly multivariable functions. Oh, yeah. That's much in your future or not, if you're not going to go very much further. Okay. And then you have problems that are a lot like example 3 on page 253. Which is exactly what we just did, except you just plug values in. So I'm not going to even do an example until you guys try it out. All right, so you got plenty of examples to go by. So let me give you this, and then I'll see if you guys have any questions here at the end. This is the practice test. You'll see in number 5 that I got really lazy. Or just, gave myself a break, whichever way you want to look at it. So, you know what I mean? Like number 1 is just bam, a bunch of derivatives. 2 is a question you should expect all the time almost. 3 is your graphing calculator kind of question. 4 is that position kind of thing from the section 3, whatever it was, with all the natural sciences in there. And then 5 is your, it's got some implicit stuff in there. It's got some word problem kind of stuff in there.
Like 3.9 stuff?
Yes, exactly. That's in there. And it's got some, I put a problem like the linear approximation problem in there. I just didn't feel like making my own up, so I figured, what the hell, I got a whole bunch of them in the review section, what am I doing to myself? So on Wednesday I'll have the answer key for this, and on Monday's the test. You're only responsible by the day of the test to be done through 310 homework. 311 homework will be due the day of the next test, it'll be on the next test.
It says in number 3, so we need to graph it, and then we need to explain like all the reasoning.
Yeah. Yeah, so will tell me why you put something somewhere. So you can say, first off, what's the very first thing you always graph when you're doing a sketch of the f prime or the dy dx? What's the very first thing you put down? If I give you, so you're going to give yourself a function because you're going to graph it, look at it. And what's the very first thing you graph when you're graphing the slope? When you're graphing y prime, f prime, whatever you call it. What's the very first thing you put down there? The most definite points. Where it's 0, where the slope is 0, right? Your anchor points. So you could just say your explanation for that would be slope is 0 at blah and blah. Do you see what I'm saying? Yeah. The reason I'm saying I'm making you do that on the practice test is because it will help you not make regular. If I force you to write the reasoning, you'll probably stay away from making the mistake of starting to just follow the function, which is really easy to do. You have to say, I'm putting it. So in this problem here, what's true about the slope back here? What's the most important aspect of the slope back here?
Slowing down.
That's one important point, because it has to approach 0, but what is it back here?
Positive.
It's positive, and it's pretty damn big here, right? But then it's approaching 0, and then it becomes negative. And then in here we got that
cup thing.
inflection point, yeah. And then So that's going to be like the lowest point, and then you're going to turn around. And that kind of makes sense because this is a cubic. So expect a squared kind of thing to come out of it. So your reasoning would be 0 is there because the square is flat. It's positive slope back there, that's why it's up there. You know, that kind of thing, yeah. Good. Cool. All right. See you guys on Wednesday.
I'm